See the answers to worksheet number 12 up on the board with the exception of number 5. We're going to go over number 5. So we won't bother giving you the answer here quite yet. Any other issues besides question number 5 on worksheet number 12 that we need to go over? 2, Sergio? 2 and 4? Okay. 2 says, how fast must an electron be traveling through a magnetic field if it follows a circular path of radius 6.5 times 10 to the minus 2? When we have a charged particle going through a magnetic field, assuming they're perpendicular to each other, the magnetic field is one way and the charged particle is moving perpendicular to that magnetic field, then we're allowed to use the hand rule for deflection, and we're allowed to use those equations that we learned over the last couple of days. The equations that we learned start with this one, F is equal to QVB. That's magnetic force equals Q times V times B. Well, then we've got centripetal force equals mv squared over r. And of course, we've got Fc equals Fm. The centripetal force equals the magnetic force. Now, we're looking for the speed of the particle here. All 3 of these equations end up having speed in there, but they don't all have radius. Typically, when you see a question involving a radius, you're going to use the combination of the 2 equations. Now, you don't have to. This is valid, but usually this isn't enough for you. Usually you end up needing to use the combination of Fc and Fm if you've got radius in the problem. Okay? If you find that it's not working for you or whatever, then just go back and try Fc is equal to mv squared over r and see what happens. This is what we're going to try first, though. Fc equals Fm, or mv squared over r equals qvb. These cancel. We're solving for the speed here, so let's take the r up by multiplying. Becomes q times b times r. And then let's take the m down by dividing. Becomes QBR over m. Q, we're dealing with an electron here, so we know the charge of the electron on our data sheet is 1.6, negative 1.6 times 10 to the minus 19, but we drop that negative. We know what the magnetic field strength is. It's 3 times 10 to the minus 3. We know what the radius is as well. We divide that by the mass of the electron, which is also found on your data sheet. And this we get off our data sheet. This and this we get from the question itself. If we do the math on that, it should work out to be 3.4 times 10 to the 7. Is that a reasonable number for a speed? If you got much more than that, you know you'd be wrong, right? If you got 3.4 times 10 to the 8, you're wrong. How do you know that for sure? Right, nothing's going to go faster than the speed of light. So even if the speed of light is 3 times 10 to the 8, 3.4 times 10 to the 8 is too big. The other one we need to go over was number 4, I think. Is that okay, Sergio? That one's good. Number 4 says, what's the kinetic energy in joules and electron volts of an alpha particle this time that moves through a magnetic field of 0.1 Tesla and follows a circular path? Once again, we've got a radius here, so odds are we're going to do the whole Fc equals Fm thing. There's no guarantees on that. It may just be Fc is equal to mv squared over r, but we're going to start off this way because 95% of the time we're dealing with the radius, this is what we're going to do. It becomes mv squared over r equals qvb. These cancel again. And we're solving for the kinetic energy here. Kinetic energy doesn't even appear here, but speed does. So let's find speed first. Q times b times r over the mass. It's an alpha particle, so we got to be careful with the charge and the mass. Look on your data sheet, but look for the alpha particle, not the electron or the proton. When we do the math on that to find speed, we get 120,300.75 meters per second. That's not what we're looking for. We're looking for kinetic energy. But if we're looking for kinetic energy, all we have to do is multiply the speed by itself to square it, and then multiply it by 1/2 m. Ek is equal to 1/2 mv squared. Somebody asked me, I think it was yesterday, oh, the equation for kinetic energy for electricity is the same as the kinetic energy for other things? Yes. Potential energy changes. Potential energy for gravity is mgh. For electricity, it's q times v. But kinetic energy is always, anywhere, 1/2 m times v squared. When we plug in the value for the mass and the speed that we just calculated, we end up getting a kinetic energy in joules of 4.8 times 10 to the minus 17 joules. There's my first answer, the kinetic energy in joules. Now we have to convert that to electron volts. I'm going to do that by setting up that ratio that I told you to set up here when we first learned what an electron volt was. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. That's equal to x electron volts over 4.8 times 10 to the minus 17 joules. The 4.8 goes up by multiplying. X ends up being equal to 300, or 3.0 times 10 to the 2 electron volts. Good? Rob, is that good? What was the issue with that? The kinetic energy or the conversion? Okay. And finally, number 5. 5 is a real tricky one, but I really like the question. Be curious once we see what the answer is, how many people got this. We want to compare two numbers, the radius of the alpha particle's path to the radius of the electron's path to the radius of the alpha particle's path. When we want to compare two things, the best way to do that is to divide them. We want to compare two things numerically, divide them. Nick, how old are you right now? 16? Okay, 16. Let's say that I'm 40. I'm not actually. I'm 41. But we'll pretend that I'm 40 for ease of calculation here, okay? So we want to compare my age to Nick's age. Nick's 16. I'm 40. We're going to say my age to Nick's age is going to be 40 divided by 16. I'm 2.5 times older than Nick is. Now, we could subtract them and say I'm 25 years older. But 25 years right now is a bigger difference than 25 years when you're 70 and I'm 95. We're both old then. So subtracting the two numbers isn't the best way to compare them, because it depends upon what stage of life we're at, how much 25 years makes a difference. But the bottom line is, if we divide them, that gives us a better perspective, because it gives us perspective for our ages right now versus our ages when we're 70 and 95. If I divide my age by your age, I get 2.5. It means I'm 2.5 times older than you are. Okay, that's quite a bit. When I'm 90 and you're 70, then I'm going to be, 1.3 times older than you are, which is not a big deal, right? It's not a huge amount. It makes more sense to do it that way than to say I'm still 20 years older or 25 years older, whatever, than you are. All right, so we want to compare two things. Let's divide them. The two things that I want to compare here are the radius of the electron's path to the radius of the alpha particle's path. So let's divide the two. The problem is I don't know what either of those numbers are. If I did, this would be an easy question. 40 divided by 16 is 2.5. Just the same as that's easy, right? I don't know what the values are. So what I'm going to do is try to put in equations for the radius of the electron's path and the alpha particle's path. We know that Fc is equal to Fm. And once again, mv squared over r equals qvb. And v's cancel. Let's solve for r. The r goes up, the qb goes down, it becomes mv over qb. Let's sub in this expression in for the radius of the alpha particle's path and for the radius of the electron's path here. We've got m electron, v electron over q electron, the magnetic field experienced by the electron. Then we've got the mass of the alpha particle times the speed of the alpha divided by the charge of the alpha times the magnetic field experienced by the alpha. There's a couple of things that cancel out right away. What are they? What disappears from this equation right away? What does it tell us is the same for the alpha particle and the electron? The speed. The speed and what? The field, right, the speed and the field. So VE cancels with V alpha. Even though they're not the same variable, they're the same value, so they cancel. The magnetic field strength is the same as well, so it cancels as well. I'm left with M over Q over M over Q. You don't have to simplify it at this point, but I'm going to. You want to divide by M over Q? Let's multiply by Q over M. So ME over QE over M alpha over Q alpha is the same as M over Q times Q over M. Now, we know the value of the electron's mass and the electron's charge and the alpha particle's charge in the alpha particle's mass. When we do the math on that, it works out to be 2.7 times 10 to the minus 4. If we divide my age by Nick's age, we get 2.5. That means the ratio of my age to his age, or the comparison, is 2.5 to 1. The ratio of the electron's path to the alpha particle's path would be 2.7 times 10 to the minus 4 to 1. Anybody get that question? Good. Good. There's a multiple choice question we're going to do a little bit later today that's not completely the same as this, but it's not unlike this either. It's fairly similar to this. So we'll see if you've kind of internalized this and you're able to do it when we get to that multiple choice question. All right, we had 8 check and reflect questions on 601 as well, 3 to 10 except for 6b on page 601. Any issues with those questions, please? All right, 4, 5, and 6 we need to go over here. The first one says, describe the key differences in how magnetic and electric fields affect moving charges. Let's first look at the speed of them. Does the speed affect the electric force? The electric force is Q times the electric field strength. Speed doesn't appear in that equation anywhere, therefore speed doesn't affect the electric force. In fact, the charged particle could be completely at rest and still experience the same electric force as that same particle would move in the same field if it was moving at 1,000 meters per second. So the speed doesn't affect the electric field strength, but the speed does affect the magnetic field strength. F is equal to QVB. Bigger V, bigger magnetic force. So a charged particle at rest experiences a magnetic force. It doesn't experience an electric force. A charged particle that's moving faster experiences a bigger magnetic force than it did before. The electric force is still there, but its value doesn't change depending upon how fast the particle is moving. What else? What about the direction of the force? The direction of the force, if you've got an electric field, is going to be parallel to the field. If it's a positive particle, it will be in the direction of the field. If it's a negative particle, it'll be opposite to the direction of the field. Either way you look at it, it's going to be parallel to the direction of the field. With the magnetic field, the force becomes perpendicular to the field. And we find the direction of the force here by using a hand rule, the hand rule for deflection, either the left hand or the right hand. So over here, it's simply positives move with the field, negatives move against the field. Over here, it's perpendicular. You're going to find the direction on a positive by right hand rule, direction on negative by the left hand rule. What about the shape of the path? Assuming the electric field and magnetic field are perpendicular to the direction of motion of the path. Here's my electric field. I introduce a positively charged particle into that magnetic field. It's going to follow a path that looks like this. If I have a magnetic field that's perpendicular like this, and I've got a positively charged particle, or a negatively charged particle, let's say, it's going to follow this path. What's the difference? What's the shape that we call this? It's a circle. What's the shape that we call this? It's a tough one. It's not a circle. It's a parabola. This is like projectile motion that you did in Physics 20. All you have acting on it is one force, and it's parallel to the field. It's downward in this case. So the path followed by that charged particle is going to be the same as the path followed by a mass in a gravitational field. Call it a parabola. Is that good for number 5? Number 6, Oh, sorry, that was number 4, I guess, wasn't it? Is that 4? Yeah. Number 5 says a positively charged lithium ion is traveling horizontally along the Earth's surface. Describe the deflection due to the magnetic force if the ion travels south to north, east to west, upward in the atmosphere. What I'd like you to do, when you get a question like this that talks about north, south, east, and west, unless you can see the mountains, unless you can see what's west and what's east and what's north and what's south, then take a piece of paper and label north, south, east, west. So north up here, south down here, east over here, and west over here. Okay, north, south, east, west on your piece of paper. And then keep your piece of paper parallel to the ground. Now, if this is north, I should label this myself here. If we've got north, south, east, west labeled like this, and I've got a charged particle that's going south to north, we'll assume that means towards magnetic south, geographic north, then which way is the force going to be? Which way is the field? The magnetic field is going from magnetic north to magnetic south, so it's going this way as well. It's going from geographic south to geographic north, right? Same direction as the particle is moving. What's the direction of the force when the particle is moving parallel to the direction of the field? 0. There is no force. Done. There's just no force. Now, what about when it's going from east to west? It's a positively charged particle going from east to west. So I'm going to stick my right thumb from east to west. My magnetic field goes towards magnetic south, or geographic north. So it's thumb towards the west. It's going to be fingers towards the north, or magnetic south. The palm is going to point which way? Downward, toward the Earth. Don't say into the page, because the frame of reference is not the page. It's north, south, east, west. We're going to say it's downward towards the Earth here. Patrick? Yeah, no, we're not assuming it's traveling. We're not assuming that it's traveling from south to north, Patrick. We're assuming the magnetic field is from magnetic north to magnetic south. So the magnetic field is this way. That's where my fingers go each time. The particle is going south to north in the first one, horizontally, but east to west horizontally in the second one, so this way. So it's thumb from east to west, fingers toward magnetic south, palm points downward toward the surface of the Earth. Let's look at C. Upward into the atmosphere. So the positive particle is going upward into the atmosphere. The magnetic field is going from magnetic north to geographic north, yeah. Magnetic north to magnetic south. Thumb upwards into the atmosphere, fingers from magnetic north to magnetic south. Palm's going to point to the left or to the west. So the magnetic force in C would be to the west. Yeah. C would be to the west. And 6, we didn't have to do 6b, we just had to do 6a. We're trying to find the magnitude of the force. The magnitude of the force for number 6 is going to be QVB. The charge of a proton is on your data sheet. The speed of the proton is given to us right there. And the magnetic field strength is 0.2 Tesla. So multiply the charge of the proton by 2.0 times 10 to the 5 by 0.2, and we should get the magnetic force there. Finally, we weren't asked to go over questions 7 and 8, but let's go over one of them. They're both real similar in nature, so if we go over one, we should be okay with the other, I think. But try number 7 first. This is a 0.2 gram metal ball. Circle that because it's in grams. With a charge of 3 microcoulombs. Circle that because it's in microcoulombs. It goes horizontally along the Earth's equator. How fast does the ball have to be thrown so that it maintains the same height during its motion tangential to the Earth's surface if the magnetic field is this? That's not unknown. It's the speed that we're looking for. Now, I told you that every time a charged particle moves in a magnetic field, it experiences a centripetal force. That's not quite true. It's a bit of a lie. If the magnetic force is the only thing affecting it, it will go in a circle. But here there's got to be something else acting on it, because we're told specifically that it's not going in a circle. We're told that it's going in a straight line. Right? It's staying parallel to the surface of the Earth, which is effectively a straight line. That tells us that we've got to have two forces, something that balances out the gravitational force. Tell me what force it is that balances out the gravitational force, Bryson. Yes, it is. That's why I asked you. Which force has got to balance out the gravitational force? Is your hand up? Magnetic force, yeah. Magnetic force. So now we've got two forces, a magnetic force acting up, gravity acting down. If gravity is bigger than the magnetic force, this thing is going to do what? If gravity is bigger, it's going to go down. If the magnetic force is bigger, it's going to go up. But it doesn't go up or down. That tells us that those two forces must be equal to each other. So we're going to set Fm equal to Fg, or QVB equals m times g. Now we're going to rearrange that equation to solve for speed. We end up getting mg over q times v. Whenever you see a question where the particle is suspended or hovering or maintaining its same position above the Earth or going parallel to the Earth or something like that, you know that you're going to have to balance something with gravity. Could be the electric force, could be the magnetic force that you have to balance with gravity. Could be some other force, but you know something is going to be equal to gravity. In this case, since it's magnetism that's causing it to experience an upward force, it's the magnetic force equal to the force of gravity. A would be similar, except that you're solving for Fg, as opposed to the speed there. Right? Good. We got a few multiple choice questions that I want to go over here today. The first two are questions 75 and 76 from your worksheet booklet. So take a look at those. The info for it is up on the board here right now, but you can't see the questions at the same time. So refer to the back of that worksheet booklet, look at 75 and 76, see what you can do with those for the next 2 minutes, and then we'll take a look at them as a class. Okay, it's time to take a look at these here now. Question 75 tells me the protons in the solar wind experience a magnetic force which way? We should, as soon as we read this question, as soon as we get to that word, circle or underline or something, the word proton, to remind ourselves that we're going to use a right-hand rule for this. Okay, we need to know whether we're using left or right hand. I guarantee you, some of you, as you were going through this, used your left hand because you just didn't really pay attention to the fact that it was a proton. Okay, as soon as you see these words, draw attention to it. Okay, it will mean, I'm telling you, it's going to mean the difference of probably 5 or 10% on your diploma exam. Little things like that. At least 5 or 10%. That's a big deal. Okay, that's the difference between, a 75 and an 80 on your diploma exam, or an 85 and a 90 on your diploma exam, or an 85 and a 95 on your diploma exam. Silly little things like that. So draw attention to that, please. Now, we get these protons that are traveling towards the right. We have a magnetic field at that point where they enter the magnetic field that's pointing upwards towards the top of the page. So we're going to stick our thumb towards the right in the direction of the particles. Our fingers are going to go in the direction of the field, and our palm, our right-hand palm, is going to point out of the page. The answer to question number 75 is out of the plane of the page. Now, question 76 tells us that the velocity is perpendicular to the magnetic field. That allows us to assume that the equations that we've learned for this are still valid. F is equal to QVB, F is equal to mv squared over r, and then the combination of them. We want to find the radius. What do we usually do when we're looking for radius? Which setup do we almost always do? Yeah, Fm equals Fc. Almost always. It's always valid, and we're almost always going to use it. Fc is equal to Fm. mv squared over r is equal to qvb. These cancel, and I end up rearranging this to solve for r. I get qb. No, I don't. I get mv over qb. The r goes up by multiplying. The qb goes down by dividing. mv over qb. I plug those numbers in, and what do I get for 76? 7.59 times 10 to the 4 meters. Now, how do we express that? They're asking me to express it as a decimal BC times 10 to the D, so I'm going to say 7.594. In this scenario, I don't fill in the decimal point. Now, had they asked me to express it as B times 10 to the W, which happens fairly often, then I would have simply expressed it as 7.59. That's the one that I do express the decimal point in. It's the same answer, just expressed two entirely different ways. All right, I'd like you to take a look at 77 and 78 here now. They're both based on the information you see up on the board on this photon-matter interaction. You read this, nothing is going to seem familiar to you as you read this photon-matter interaction. That's okay. I'm giving this to you on purpose to illustrate that it doesn't matter if any of it seems familiar to you. You boil it down to what matters. Boil it down to the concepts that do seem familiar to you and solve the question that way. Okay, give you a couple minutes, then we'll take a look at it again. All right, time to take a look at this one now, please. Number 77. Says the curved paths of the particles in the pair production diagram result from the electron and the positron moving through an external magnetic field. In this diagram, the external magnetic field is going to be which way to cause the path shown in the picture. How do we do this? There's two charged particles in a magnetic field here. It's the same magnetic field causing both of these particles to curve, but both of them are curving in different directions because they're opposite charges. One's positive, one's negative. One's curving upwards as a result of the field. The other's curving downwards as a result of the same field. What we need to do here is pick one of those particles. It doesn't matter which one. Let's pick the positron. It's a positive particle that's initially moving to the right. What direction is the force acting on that positron if it was moving to the right, but now it's curving upwards? Which way does the force need to be to curve it upwards? No. Which way does the force need to be to curve it upwards? The force needs to be upwards, right? The magnetic force acting on it is going to be upwards. Now, we've got a positive particle moving to the right. We've got a force upwards. So we're going to say hand rule for deflection, but it's going to be right hand because we've chosen to use the positive particle. And we're going to do some algebra, for lack of a better term on it, because we're looking for the direction of my palm as opposed to the direction of my fingers as opposed to the direction of my palm.
Why would it be attracted upwards as a positron or whatever?
Yeah, no, okay. Yeah, no, you're right. Okay, it's a good question, Nick. Nick's asking, why would it be pushed upwards? Because these two are oppositely charged. Shouldn't they attract each other? Yes, electrically they should attract each other. But there's a force that's bigger than that force of attraction between this positron and this electron. And that thing that's bigger is the magnetic force. They're telling us in the question that the magnetic force is causing the positron to go that way and the electron to go that way. So that magnetic force must be bigger than the electric force that's causing them to be attracted to each other. We don't even really need to pay attention to the electric force because this question isn't about that. But you're right, Nick, there is one there. It's just not big enough to pull these two together. It's not big enough to win out over the magnetic force. So you got a magnetic force acting on this positron that's upwards toward the top of the page. It's moving to the right, so we're going to say thumb to the right, palm upwards. The fingers, which point in the direction of the magnetic field, are into the page. Now, what if you had picked the electron to analyze? If you had looked at the electron to analyze, we're going to have a negative particle moving to the right, and we're going to have a force pushing downward on the electron, causing it to go downward. We're going to stick our left thumb in the direction of the particle, our palm downward, our fingers are still going to point into the page. So it doesn't matter. Any way you look at it, the magnetic field has to be into the page in order to cause the electron to go that way or the positron to go the other way. The answer for question number 77 is going to be A, into the page. Now, it goes on to say during pair production, the speed of the electron or the positron can be calculated. What's the equation that we use to describe the speed? Well, Fc is equal to Fm. We say mv squared over r is equal to qvb. And we say v is equal to, v's cancel there. R goes up by multiplying, m goes down by dividing. Becomes qbr over m. And the one that matches up closely with that is this one, bqr, qbr, same thing. What's A? Two more questions that I'd like you to do here right now. 80 and 81. See what you can do with those for the next 2 minutes. All right, let's take a look at questions 80 and 81 here now. A proton with an energy of 894 electron volts. Right away we see that electron volts, we circle that because it's non-standard units. Travels perpendicular to this magnetic field with this radius. We want to find the speed of the proton. Tell me please, show of hands, how many people did exactly the same thing as I did the first time I went to do this question? As soon as I saw this, I said, oh, it's going in a circular path, this radius, we want to find the speed. I'm going to say Fc equals Fm, and therefore mv squared over r equals qvb. How many people did that? How many people tried to do that at least? Okay. There's nothing wrong with that. That's a perfectly valid concept to solve this problem. The only problem is it doesn't help me get what I want to get. I don't know what the speed is. Clearly, I'm looking for the speed, so I don't know what it is. Nor do I know what the magnetic field strength is. So I'm not able to use this equation to solve for two unknowns. What I have to do is look a little bit closer at some of the other things that apply here. For instance, we have the kinetic energy of this proton. It's 894 electron volts. We know that kinetic energy is equal to 1/2 mv squared. If we want to find the speed, all we have to do is rearrange it to solve for speed. It becomes 2ek over m. Now there is a little bit of a problem here, and that is that I don't know what my kinetic energy is in joules. I got to find that. So we're going to say 1 electron volt over 1.6 times 10 to the minus 19 joules equals 894 electron volts over x joules. The x goes up by multiplying, the 1.6 goes up by multiplying. And I get a certain answer for my energy in joules, which I plug into there. When I solve this, I end up getting A, 4.14 times 10 to the 5 meters per second. How do we know right away that C and D are wrong? What tells us that C and D can't be the correct answer? They're faster than the speed of light, 3 times 10 to the 8 meters per second. So it's got to be A or B. Turns out it's going to be A as a result of this analysis. Now, once we've found that speed, we're looking for question 81, the strength of the magnetic field. Now I have the speed. Now I can solve for magnetic field. I can use what I was going to use in question A. I can use that down in question B. Just rearrange to solve for B. It becomes mv over qr. Do the math, and we get what we get. Nick, question? I'm not sure. What does that end up being in joules, guys? 894 times 1.6 times 10 to the minus 19. What is it? 1 point times 10 to the negative 16? Is that what you got, Nick? I think you might have entered an exponent wrong or something. 894 times 10 to the minus 19 is going to give us, not going to give us 10 to the minus 18, right? So just double check that again on your calculator and let me know. One more multiple choice question here, okay? And then we're going to do a little bit of new material here today. Take a look at this one, see what you can do. think back to the worksheet question that we worked on, worksheet number 12, question number 5. Use that as a basis for solving this question, okay? Okay, last multiple choice question. Let's take a look at this one now. The ratio of the radius of the alpha particle's path to the radius of the proton's path. Ratio is like compare. We talked about comparing my age to Nick's age earlier in the class. 40 divided by 16 is 2.5. It means I'm 2.5 times older than him. That's a good comparison of our ages. If we wanted to find the ratio, we'd do exactly the same thing. 40 divided by 16 is equal to 2.5. The ratio of my age to Nick's age would be 2.5 to 1. So we want to find the ratio of the alpha particle's path to the proton's path. We're going to divide the two just the same as we did when we were asked to compare the two. Radius of the alpha particle's path, radius of the proton's path. Now, the radius we said was mv over qb. So the radius of the alpha particle's path would be m alpha, v alpha, q alpha, b alpha, over the proton's path would be mp, vp, over qp times b for the proton. Now the magnetic field is going to be the same regardless of which particle you're talking about. The speed is not quite the same. Rather, the speed is twice the speed. The mass of the alpha particle is actually 4 times the mass of the proton. The speed is twice the speed of the proton, and the charge is twice the charge of the proton. The proton is just mv over q. You can put numbers in for these masses and for these charges if you want, but it makes it a lot easier here if you just cancel things out. mp cancels, vp cancels, qp cancels. I end up with 4 times 2 divided by 2 gives me 4. So if R alpha over Rp is 4, then the ratio of the two is what? 4 to 1. The answer is going to be C, 4 to 1. So we did, in essence, what we did in that worksheet number 12, question number 5, except we didn't need to put all the numbers in here this time because we had some nice convenient things that would cancel each other out. Nick?
Is it right to break down x squared over r and then for the proton instead of 1 for v and 1 for the alpha, but if you do double and just figure it out like what it would be?
Say that again. What did you do?
Like for the proton instead of 1 for v and for the alpha.
No, but go back a step there.
I just wrote down mv squared.
So you just wrote down mv squared over r.
See how it affected the proton. I just like plugged in a random number for v.
And to see how it affected r, or see how it affected this overall number. This overall number, you mean? Okay, you got to be careful with that, Nick. You got to be careful with that. Guys, pay attention to what Nick just asked. It's a good question, Nick. You got to be careful with that. In this situation, in some situations that will work, in some situations it won't. The reason it won't work here, the reason it's not valid, although you might get the right answer by coincidence, the reason it's not valid is because you're then comparing forces, not radius. Does that make sense? Now, if you're dealing with something like r squared, well then your number is going to be completely different than if you're dealing with f, right? Here you've got f and r, so you might actually get the same answer, but it's by coincidence. If the equation was different, you wouldn't get the same answer. You're dealing with, you tried to find the effect on force. We're not trying to find an effect on force here. We're trying to find the relationship between the radii, not the forces. Okay? All right, I want to do a little bit of new stuff with you today, but not a great deal. This is going to go back to the lab that we did on Friday and on Monday. We talked about a wire that carries an electric current going through it. That electric current is really just a bunch of moving electrons, and when that's exposed to an external magnetic field, it will experience a magnetic force. The reason it does is because the charged particles that are moving through that wire experience the force. Those charged particles through that wire are what we call an electric current. Specifically, the current is the rate of flow of electric charge. A lot of people get speed and current mixed up. The speed of the electrons in the wire versus the rate of flow of the electrons in the wire. It sounds like it's almost the same. Well, it's analogous to this. You're standing on the side of a highway with a radar gun as a police officer trying to get speeders. You're measuring the speed of the cars that go by. Your friend is standing beside you on the side of the highway, not measuring the speed of the cars. He stands there with a stopwatch and a piece of paper to keep a tally of how many cars are going by per second. You measure the speed of a car to be 144 kilometers per hour. Traffic is moving really, really fast. But there was only one car that went by per second. The speed is high, but what's analogous to the current is low, because there's only one car per second going by. Next day you go out there, the speed of the cars are only 62 kilometers per hour. There's a bit of a traffic jam. But there's 13 cars per second that are going by you. In that case, the speed is low, but what's analogous to the current is high. Current is not the same as speed. Sometimes they can both be high, sometimes they can both be low. But they're not the same thing. Current is not how fast the particles are moving, but rather it's how many coulombs are moving per second, the rate of flow of charge. The symbol for electric current you learned on Friday was capital I. If it's the rate of flow of charge, then it's going to be Q over T. The units would be coulombs per second, right, Q over T. But a coulomb per second is exactly the same thing as an amp or an ampere. Let's do a quick little easy example here. This one says calculate the current in a wire through which 20 coulombs of charge passes in 4 seconds. We're looking for the current, that's capital I. We've got the charge, that's Q. We've got the time, that's 4 seconds. The equation, the simple equation, is Q over T. 20.0 coulombs over 4.00 seconds. We divide those two and we end up getting 5.00. What would the units be for this? Amps, or if you forget that unit, amps, that's okay. If you forget that units, you can always go with the equation and say it's going to be coulombs per second. 5 coulombs per second or 5 amps. Either way works. Doesn't get a whole lot easier than that. Now, generally, if you do get a question with electric current, and I believe there is one on your test coming up on Monday, yeah, one with electric current, then generally it's going to be in some kind of context. So it won't necessarily be harder than the question you see up on the board, but there might be a half a page of information that goes along with it. That makes it, at least it seems to make it harder. Okay? Don't let it make it harder. Okay, if you're dealing with current and charge and time, then just turn it into a simple question just like this. All right, take a look at these two, please. I'll give you about 1 minute to answer these two questions, and then we'll finish off with a little bit more new stuff. Last little bit here, guys, and we'll wrap it up just after this here. The whole point of talking about electric current in our magnetism unit is so that we can understand what happens to a charged particle in a wire as that wire is exposed to an external magnetic field. An electric current is just a bunch of moving electrons. If they're exposed to a magnetic field outside of a wire, then they'll experience a force. If they're exposed to a magnetic field inside a wire, then they'll also experience a force. When they're outside of the wire, they want to go in a circle, so they will. The magnetic force will cause them to move in a circle. While they're inside the wire, they want to go in a circle, but they can't, because the wire keeps them from going in a circle. Instead, what happens is this. When the charged particles are inside the wire, i.e. when we have an electric current, that wire itself will experience a force as a result of the individual electrons within the wire experiencing the force. We can find the magnitude of the force by the equation that I taught you when we did the lab. We can find the direction of the force by using the hand rule for deflection. If the force on an individual electron within the wire happens to be, say, down, then the force on the wire itself will also be down.